All right, in this question, we have a loop of variable size based on this graph over here, the change in the area of the loop based on time, and the loop is placed in a constant electric field, and we want to know the potential difference around the loop at two different points in time, t equals 1 second and t equals 4 seconds. The objective that this question satisfies is I can use Faraday's law to calculate the EMF associated with the Curly electric field. So we're going to use the form of Faraday's law. Potential equals negative magnetic flux over dt, or negative d magnetic flux over dt. And in that case, that's going to be negative d over dt times the magnetic field times the area times cosine of theta, in this case, which that goes to 1 because theta equals 0. So at t equals 1 second, we can see, if we go back over here, if this is t equals 1 second, in this time frame denoted by the pink part of the grid, we can see that area is constant. Therefore, this just the negative d over dt is not going to be relevant, so we just have potential equals negative 15 teslas because that's our magnetic field times 4 meters squared, because you can see that's our area at t equals 1 second, and that's going to equal negative 60 volts. Now, in the case of t equals 4 seconds, if we go back to our graph over here, if we look at the yellow highlighted portion, the area is obviously changing with respect to time. So then we are just going to use a simple y equals mx plus b equation, assuming that this yellow vertical line here is our new, like this point is our new origin. So this is our new y-axis. To calculate the slope of this line, because this portion is no longer relevant. So that's going to mean area E is equal to negative 4/3 t, our slope, plus 4, our y-intercept. T equals 4 seconds here. Okay. So then our new we will still use the same equation, potential equals negative d over dt times magnetic field times the area. In this case, we cannot dismiss this negative d over dt now, so we can for the magnetic field because it's constant. So we have negative 15 teslas times d over dt times negative 4/3 t plus 4. Taking the derivative of that, we get negative 15 teslas times negative 4/3 meters squared, we get 20 volts. In this case, the magnetic field is constant, so it doesn't induce a current. The current is constant.